everyone. Welcome and thank you for joining us for this presentation, Validation Challenges for the New 5G RAN Transport. My name is Liz Garcia and I am your host for today's event. Your presenter today is Avik Bhattacharya, Product Manager for Network Infrastructure Validation at Keysight Technologies. Avik has worked on cutting-edge networking technologies including routing, switching, multi-protocol label switching, software-defined networking, and time-sensitive networking. As an expert in TSN and automotive, industrial, and 5G RAN networking testing, he is frequently a presenter for technical events and a contributor to technical blogs and articles. So Avik has a lot of info to share with you on today's topic. And here is a look at today's agenda. What's not highlighted here is the Q&A session at the end of the event. If you have any questions during this presentation, please type those into the chat window and we will see those on the back end and answer them at the end of this event. Your questions are anonymous, so the other audience members cannot see them, but we will be able to see those on the back end and we'll again answer those at the end of the presentation. And without further delay, I will pass the mic to your presenter. Avik, the floor is all yours.
Thanks, Liz, for the introduction. Hello, everyone, and welcome to this session where I'll try to share some of my experiences with 5G network operators and equipment vendors about what are the challenges they are facing in designing the transport network for 5G. So in today's world, the network designs are driven by what the applications need. And as the 5G era ushers in, the demands for new services like the low latency connected cars, bandwidth hungry video applications, and also like IoT are expected to see massive increase. And to classify these applications better, the rollout of 5G will provide benefits in three major areas, and which is also known as the 5G triangle. And this consists of the EMBB, or the enhanced mobile broadband high-speed use cases. Then we have the MMTC, or the massive machine type communication, or the IoT use cases. And finally, URLLC, or the ultra reliable low latency communication use cases for the industrial automation. A key to making these services work will be to design capable platforms to supply high-end computing and ultra low latencies that is required. The clouds are becoming more distributed in nature, offering superior performance and throughput, and we have edge cloud and the cloud radio access network, or the RAN platforms, which are like which will be vital to support advanced and immersive technologies like this. So there are options for combining edge cloud with cloud RAN to provide extremely low latencies and also improve operational efficiency and like do automation, flexibility, and programmability, and also like cut the time to deploy these immersive services that we talked about. With 5G, more operators are interested in moving to a flexible cloud RAN architecture. The functional components of a 5G cloud RAN architecture are the RU, DU, and CU. And in a classical 5G RAN architecture, the BBU functionality is actually split into two different functional units, like we discussed, a distributed unit, or the DU, which is responsible for real-time L1 and L2 scheduling functions, and the centralized unit, or CU, which is responsible for the non-real-time higher layer 2 and layer 3 functions. This CRAN enables the operators to address different application requirements by locating the storage and the compute resources at either at the base of the cell site or maybe hundreds of kilometers away from the cell site, or maybe anywhere in between, like we can see in the slide. For example, the operators can support latency sensitive applications using the multi-access edge computing data centers that are located closer to the serving cell site. The transport network between the RU and DU is known as the fronthaul, between DU and CU as the midhaul, and between CU and the gateway is known as the backhaul. So in the network design, the DU's server and the relevant software could be hosted on a site itself, or it can be hosted in an edge cloud, like a data center or a central office somewhere, and it's depending on the transport availability and the fronthaul interface. The CU server, on the other hand, and also the relevant software can be co-located with the DU, or it could be hosted in a regional cloud data center. The actual split between DU and RU may be different depending upon the specific use case and implementation. And then there could be both standalone and non-standalone deployments with 4G and 5G technologies. The technologies will need to coexist in the same RAN. So there are a lot of design considerations that goes into selecting the right networking technology. And these are the 6 pillars of 5G RAN transport infrastructure as we see it. Time synchronization, deterministic transport or TSN, ECPRE, security encryption, SDN, and virtual infrastructure. And let's get deeper into some of these areas and identify the challenges related to adoption. With all of these new and existing technologies, validation and benchmarking is the key here. So latency is a very important characteristic of the fronthaul network. And to understand why, let's take a look at how the functionality splits are done between the DU and the RU. At the top of the stack in the slide, we have the IP packet, and at the bottom of the stack, we have the antenna. As we move from the IP to the RF, the bandwidth requirement increases with more encapsulations being put on the data. But at the same time, as we move down the stack from IP to RF, we also have lower latency tolerance. For example, an IP packet is not really latency bound, but a radio clocking signal needs to be within a low latency limit. As per the 3GPP standard, the 5G network, the 5G network is designed with a higher layer split and a lower layer split, where we separate the real-time data and the non-real-time data. And because of this lower layer split, the DU sends and receives IQ samples to and from the RU in ECPRE encapsulated frames. These IQ samples are time critical in nature and consumes bandwidth much more than the actual user data. Naturally, a fronthaul transport network must be designed in a way to minimize loss and delay while carrying the high bandwidth traffic. So these are the permissible latency values that is standardized by the 802.1cm standard for the fronthaul network. And we can see that between RU and the DU, the one-way latency is 100 microseconds, which means that if a fiber introduces 5 microseconds per kilometer, then this gives a budget of 20 kilometers. But we also need to consider the delay introduced by the switching elements in that fronthaul. And as we can see, for the midhaul, it's a bit relaxed compared to the fronthaul. So frame loss allowance for different class of services are also different. While the user plane and control plane data can tolerate up to 1 frame loss in every 10 million frames, tolerance of M plane data is up to 1 frame loss per 1 million frames. Latency is also bounded in fronthaul network, which might be very stringent for something like URLLC services. And depending upon the use case, latency tolerance in fronthaul network can vary. So required fronthaul bandwidth also depends on total channel bandwidth. It could depend on the MIMO layers, number of sectors, etc. And depending upon the need, either 10 gig or 25 gig or 100 gig links are used. To solve this latency problem, 802.1cm also recommends the use of strict QoS priority and TSN, frame preemption mechanism. The fronthaul traffic or the ECP user data traffic is treated as express, and other traffic present in the network is treated as preemptible. And all the switching elements in the fronthaul network needs to support the frame preemption capability in this type of networks. The validation engineers need to ensure it works at a network level to avoid consequences such as like too much of frame loss causing the OFDM symbols not being sent on the user interface, the AR interface, or maybe a late arrival of a frame at the RU causing expiry of the time slot for that symbol. The fronthaul transport network consists of Ethernet switches or routers, and validation is needed for each such node in the network, as well as for the whole network, to qualify overall quality of the service here. To validate such a system under test, the DU and the RU can be replaced with the IXNetwork Ethernet test ports and the relevant interface speed, such as 10 GigE or 25 GigE. Similar test topologies can be created for mid-haul or even backhaul by connecting the IXNetwork Ethernet test ports using the link speeds of 100 GigE or even beyond. The test is performed in typically 3 logical steps, where at first we configure the test parameters in IXNetwork software, and then we run the test simulation and finally verify the results and measure different parameters. Now moving to the next part, traditional Ethernet is designed on the concept of best effort delivery, which doesn't guarantee the bounded latency that we talked about. A large but less critical frame in transmission can make a time critical frame wait and therefore increase its transmission latency. Frame preemption technique allows the bridges to pause transmission of non-time critical frames when a critical frame is just about to egress, and the transmission of that less critical frame can resume afterwards. Frame preemption is a new technology, and that's coming into this switching hardwares. And while adopting this technology, the network designers, they need to think if all components are working properly, starting from adherence to the QoS priorities or the fragmentation and even the reassembly that is being done for the fragmented packets. And finally, if the frame preemption is able to ensure the end-to-end bounded latency or not, which is the end goal for adopting this technology. Preempting a non-time critical traffic sometimes can actually result in erroneous fragment generation. And in this type of implementations, which are improper implementation, this can cause a lot of consequences, such as a switch can generate erroneous fragment, which can jeopardize the time criticality of the fronthaul network. Or maybe while preempting, the preempted frames can suffer from added overhead or inefficient reassembly implemented in the switch. To validate frame preemption, the switches can be connected with IXNetwork Ethernet test ports with relevant interface speeds such as 10 gig or 25 gig. And one of the important tests to be performed is to measure the latency of the express traffic in presence of preemption. This can be performed by using IXNetwork test ports to generate both express and preemptible traffic. And the receiving test port can check for proper fragmentation done by the switch and also measure if the express traffic latency is within the limit. So the switch vendors that we have worked with, we have seen they also need to validate the reassembly function. And this can be done by using the IXNetwork test ports to generate preempted fragments and measuring the integrity of the reassembled frames by the device on the receiving side of the topology. IXNetwork TSN Wizard provides an easy way to configure the traffic mix in this type of scenarios. And what we have seen is this is extremely popular with the network engineers because they can configure individual traffic flows, they can configure the VLAN priorities, or they can while validating the reassembly function, they can control each and every fragments, for example, to design a test. And each fragment can be changed to represent an erroneous condition. Now let's talk about a little bit on the interface speeds which are being used to design the fronthaul networks. We have talked about the different split options earlier in context of understanding the latency requirements of the fronthaul. We have seen that as we move from IP to RF, the bandwidth requirements increase, and with more encapsulations being put on the data, the extra encapsulations are actually for providing redundancy, protection for errors, retransmissions, etc. Now, looking at the specific radio scenario and comparing the bandwidth required by different option splits, the 5G eCPRI scenario shown here, it has a requirement of 20 gig of user data and 10 gig of control data. And this is like one of the example scenarios, I would say most common scenario. And in most of the cases, the bandwidth requirements are going to be in the similar range for the transport network. The 5G fronthaul switch manufacturers are therefore looking at 25 gig interfaces for the best utilization of the pipe. While connecting towards the RU, they can use the 25 gig link, and while connecting towards the core, the links can get aggregated to 100 gig or beyond in some cases. So the switches are getting designed to support different link speeds, 10 gig, 25 gig, and 100 gig to be able to build up the transport network. And to support these speeds, the switches need to operate with QSFP28 as well as SFP28 connectors. The optics may be single mode, multi-mode fiber, and the cables could be long, especially in case of fronthaul. We have seen 25 Gbps LR optics. So in order to validate all these different link speeds and optics, we need a test tool that supports all of these connectors, as well as traffic and protocol scale on top of these physical connections. The Novus S module is designed for these 5G RAN transport test cases. Now, as we move on to the next technological pillar that enables 5G RAN, we come to the adoption of existing CPRI protocol over Ethernet to carry the radio data. And we touched upon this a little bit while discussing the time criticality requirements a little while back. So the fronthaul for 5G uses eCPRI protocols, which is basically adaptation of the 4G CPRI protocols for Ethernet-based networks. The existing CPRI do not scale cost effectively for 5G because of its use of much larger spectral bands and massive MIMO, etc. The CPRI Corporation has actually created an enhanced CPRI or eCPRI protocol that scales bandwidth about 10 times more effectively than 4G CPRI, and thus optimizing the transport bandwidth. So all the radio samples or IQ data, real-time controls, and some other services data can be carried over eCPRI encapsulation, as you can see in the slide. And for a non-standalone deployment, the 5G eCPRI and 4G CPRI transport may coexist. And in such scenarios, the 4G CPRI data is encapsulated over Ethernet, called the radio over Ethernet. The fronthaul switch manufacturers need to support both in their devices for being used in such kind of non-standalone deployments. As we have seen in the previous slide, that eCPRI can work on different transport layers like TCP, UDP, or even over layer 2 directly. The network engineers need to test, and they need test solutions to validate all these combinations. And not only the data plane, but eCPRI introduces services and, for example, different OEM messages as part of the specification. The IxNetwork eCPRI solution can help emulate eCPRI nodes and generate traffic, both legitimate and malformed. It's being widely used to test the eCPRI messages as well as functionalities like delay measurement, etc. The 5G transport network also imposes a very strict time synchronization requirements on the network. And let's discuss a little bit why. The fronthaul interconnects radios to the core, and the synchronization requirement is driven by what the radio needs, right? Because it's all radio data. And based on the need of the radio, there are classifications of the timing requirements for different scenarios. The different classes allow different amount of timing error that is in propagation, when using a time synchronization protocol. Now, timing error is the amount of error that is introduced in the synchronization signal all the way from the signal source to the consumer of the signal. And this table that we see in the slide, it kind of describes how the synchronization requirements are driven by what that 5G use case is. That is, what that radio is doing. For example, for a basic radio feature like TDD or LTE coordination protocol, the allowable time error is 1.1 microseconds between the grandmaster and the radio unit. And this is considered like one of the relaxed scenarios. More advanced scenarios like carrier aggregation, which is a technique where you use multiple carriers or RUs to serve a single cell phone. In this type of cases, the radios require more coordination between them, and the maximum admissible time error becomes lower and lower. Note that in the above network, it's a DU and the RU which performs the real-time radio operation and needs to be synchronized. The CU does not do any real-time radio function and therefore does not have the strict time sync requirement that we are talking about right now. In a tighter time budget scenario, the DU typically will have a GPS input and will serve as a 1588 grandmaster for the RU or the RUs that it is serving. So every hop needs to support the timing. That is, every router in between will need to be 1588 boundary clock or a transparent clock based on the design. And also sync key is implemented here in this type of networks to improve the stability of the frequency base. So also note that the timing signal in this type of scenario will have to traverse the routers and the time error gets accumulated across every router in the path. As all of these routers will introduce some time error, they are classified based on their accuracies. For example, a class C router will need to comply with the error introduction of maximum of 10 nanosecond. So validation and benchmarking of the synchronization plane is absolutely must to ensure the network does not exceed the time error budget, and the different 1588 profiles need to be also tested for conformance. And also at a network level, the engineers need to ensure that the synchronization plane is not disturbed by anything else. For example, it's not disturbed by an unexpected bursty traffic or high user plane traffic scale. IXNetwork provides PDP emulation based on the 1588 v2 standard and ITU-T G8265.1 telecom profile. And IXNetwork can actually emulate master clock, slave clock, and like a transparent clock. It supports all transport mechanisms such as Ethernet VLAN, IPv4, and IPv6. It also supports a comprehensive PDP feature set such as multicast, unicast, mixed multicast, unicast, one-step, two-step, delay request response, peer delay method, etc. More importantly, the telecom profiles are built into that IXNetwork PDP solution. On the other hand, it's also important to validate some of the components of sync key, especially the ESMC protocol. The ESMC protocol is the one that helps in clock management, distribution, and traceability, and it's equally important to validate in all those type of functions. Okay, so I can already see a few interesting questions coming in as we move on to some of the most popular buzzwords of the 5G era in the remaining part of this webinar. So we'll start with network slicing. So the demands for new services like low latency connected cars, bandwidth hungry video applications, and IoT, they are expected to see a massive increase. And we started our webinar with this today. But these services require strict service level agreements, which requires dedicated end-to-end channel for each of these services. And the existing networks are not equipped or even scalable enough to support these type of demands. So while designing these networks, this thought was never put. Now the solution right now is solution to realize this full extent of the 5G performance to enable all these applications is network slicing. And network slicing allows the creation of isolated end-to-end network with specific quality of service, which are then used to provide that required SLA that we talked about. The packet-based 5G transport network can either be MPLS based or IPv6 based, depending upon the network design. And routing protocols like ISIS, OSPF, and BGP, or anything else, they could be used to provide network reachability within fronthaul, midhaul, or the backhaul part of the transport network. So the segment routing works with all these protocols. And that's the key enabler to provide the slicing infrastructure in the 5G transport network. There are various technology choices being discussed to enable the network slicing in the transport network. Operators will eventually, they are going to evaluate different options and select the technology based on the use case and their own infrastructure as well for the best service offering. And they will see which of these technologies are providing operational proficiency. So the validation is the key for the network design here. Vendor selection, field trial, all the way to the deployment, validation is absolutely important. The network engineers need to ensure that proper provisioning is happening and interoperability is also present while using these segment routing technologies. IxNetwork has most comprehensive coverage of segment routing protocols, starting from ISIS, OSPF, BGP, SR. It supports the centralized provisioning and the policy controls through PSAP or NetConf-YANG or any other methods. And at the same time, one of the recent techniques getting debated for being used for network slicing, that is Flex Algo, also can be validated using IxNetwork. The coverage is not only limited to IPv4, and it actually expands to IPv6 as well. To move ahead, we have also seen many interoperability issues in the field as these are new protocols being implemented on evolving standards. So different vendors are coming out with their own interpretation of the standard and their own implementation. And you as a network equipment manufacturer, you don't want your equipment to be non-interoperable just because the implementation team missed a clause in the draft or interpreted a clause differently. The Keysight customers are using IXANVL conformance package for segment routing heavily to isolate these type of problems in very early stage of their implementation and avoid the consequences in the field. Now, finally, today we are going to talk about the security aspect of the RAN transport. We have discussed that the RAN needs transport data. The RAN needs to transport this data from the radio antennas to and from the 5G core network. And as we have seen in the previous slides, this network is designed to carry high throughput and low latency using ECPRE. If the fronthaul networks are deployed in unsafe domains, which is going to be in most of the cases, and in this case, end-to-end security system should be implemented to protect the data flow here. So according to the specification of the ECPRE, the vendors may optionally implement different encryption technologies like MACsec or IPsec. However, these encryptions impose additional processing overhead on the network elements. And the switch vendors, they need to optimize the implementations of the security protocols so that the latency requirements of the 5G NR radio is met. Which technology to be used for encryption is an open subject right now, and it's being debated in forums like the ORAN Alliance and other forums. But one thing is very evident, that benchmarking the performance of these encryption techniques is extremely critical to successful adoption. And this is in addition to the validation need for the encryption algorithm, key generation techniques, and the protocol functionality. So IxNetwork is the only professional validation solution available today to validate MACsec on different interface speeds, ranging from 10 gigi to 400 gigi. And it can validate the key negotiation and distribution at a high scale, and very importantly, measure the forwarding performance during a rekey event. The conformance testing for these security protocols is also very popular. And an IPsec stack being integrated into a RAN transport switch need to go through proper conformance testing for different algorithms, for example, ESP. So for this, IXANVL is another tool which is widely used and which has an IPsec conformance test suite consisting of more than 700 tests, for example. So as we reach to the end of the webinar today, let's try to articulate our learnings or key takeaways from this session. We have seen that the 5G RAN transport is a complex ecosystem trying to solve application needs. And a combination of new and existing layer 2-3 technologies can solve these problems and help design the network infrastructure. So there is a lot of debate around which technology is more efficient than others, and also a lot of experimentations and discussions is going to continue. However, both for the vendors supplying the network equipment or for the operators deploying these networks, validation and benchmarking is the key to successful adoption. Okay, so over to you, Liz, for the next part.
Thanks, Avik. I am really impressed with all the information you provided in such a short amount of time. Thank you so much for walking us through all of that information. Now it's time for the question and answer session. I'm going to give Avik some time to look at the questions that came in during the presentation and take this time to remind the audience that it's not too late to ask your question. So please use the Q&A chat window to ask any question you may have. If we do not get to your question during the session, we will follow up via email after the event. And we would really appreciate it if you take the survey before you exit. We really take your feedback to heart and we'll implement it into future events. So please take a moment to answer the survey. We really appreciate it. And we have quite a number of additional resources for you to check out. There is a resource widget within your console. So if you navigate to that widget, you'll get direct links to additional reading. You can also download this PowerPoint and we'll have these assets hyperlinked. But again, a lot of great resources for you to dive a little bit deeper into this topic. Okay, so I will actually kick off the first question. I saw one that came in earlier and highlighted it, and then I'll let Avik pick the questions that he wants to answer after this one. So first question is, you have talked about frame preemption in the Fronthaul network. How necessary is that? Does it make sense to implement such a complex technique? And how much is the return? What do you think, Avik?
Yeah, so that's a great question. And I think the answer is depends on the application type and needs. So taking reference from the ORAN Fronthaul architecture, it recommends not to use Jambo frames, where there is a need for bounded latency for time-critical traffic, mainly EC-pre IQ data. Now, the reason is use of Jambo frames is normally avoided as they can impact the overall latency of the network. Frame preemption comes in as a solution, assuring bounded latency for Fronthaul traffic in presence of Jambo frames. And also important to note here that the effectivity of the frame preemption diminishes with the higher link speeds. So we have seen vendors implementing frame preemption on 10 gigi and 25 gigi, but normally avoided in the 100 gig implementations. So next question, did the time synchronization needs change from 4G to 5G? Well, the time synchronization need really didn't change, but as I mentioned earlier, that the application type defines the accuracy of sync between the nodes. For example, an URLLC use case for industrial automation that requires more stringent response time from the network. And for a carrier aggregation use case between two RUs, the two RUs need to be in sync within certain limits. So also 4G, used CPRI as the radio data transport. Now, one of the differences between CPRI and eCPRI is that eCPRI does not carry the time synchronization. So in 5G with eCPRI based Fronthaul, time synchronization is done separately through 1588 or SYNCI or both. Next question, does the Keysight tool support 1588 testing over 1 gig link speeds? What about higher speeds at the backhaul side? Yes, it does. Keysight has different load modules for different speed modes. The Novus module that I have shown during the presentation today is specifically built for most popular IXANVL speeds and optics. That is the 10 gig, 25 gig, and 100 gig. But the same IxNetwork test solution can work on other Keysight hardware as well, which provides 1 gig and on the higher side up to 400 gig. So this is not specific to only 1588, but applies to all the other protocols as well, which are relevant for RAN transport testing. Next question, do you support the ORAN Alliance specification? So first of all, Keysight is very much involved in the ORAN Alliance and one of the contributors from the test specification perspective. Some of the things that we discussed today falls under the ORAN Alliance Working Group 9. That is, it's under their purview. And so Working Group 9 is dealing with the transport network architecture for Open RAN. And the answer to your question is yes, absolutely yes. We support testing, the architecture being discussed there. And of course, we can get into details if you have any interest in any of the specific use cases. Please reach out to our teams and we can discuss more.
Thanks, Avik. I'm going to cut you off there and ask that you respond to any other questions that came in via email. So thank you everyone in the audience who participated and joined us for this presentation. We really appreciated you asking questions and again filling out that survey. If you're interested in more content, we have a lot of webinars, so check out the link on your screen for more information in this series. We hope to see you again at a future event, and we hope that you have a great day. Thanks again for joining.